All I'm going to say really about the existence of RK, I'm not going to discuss at all how one constructs this RK, but maybe I'll make a remark. We have this RK from AK star over K star, surge X onto gal K ab over K, right? And we know the kernel. And so therefore we know the group gal K ab over K. But I just wanted to kind of make it, it's nice to know what we know and what we don't know. So I think it might be worth just formally remarking that we don't know. In general, however, we don't actually know K ab. So we know this Galois group, but we don't know what one of the fields is. It's slightly ridiculous when you think about it, isn't it? Because the point is, you know this Galois group is the abelian. You know gal K bar. You know what K bar is. I mean, yeah, you know that K bar exists, and you know what gal K bar over K is. So there's a group, and we can take its abelianization, and we can talk about that abelianization. And so if you do it that way, then if you don't explicitly invoke the fundamental theorem, then you never have to worry about what K ab is explicitly. So K is Q, or imaginary quadratic. K ab is known. So there's an article by Sayre in Cassels-Froelich, not the canonical article by Sayre. Sayre's other article. Sayre's other article in Cassels and Froelich. So for imaginary quadratic fields, it's to do with J invariance and torsion of CM elliptic curves. So I've given you this terrifying thing, and I think I owe you an explanation of what this field looks like, of what this gadget looks like. So let's analyze it, right? K equals Q. Let's analyze AK star over K. Let's analyze AQ star over Q star. Okay, because I've presented this as some terrifying group that we don't really know too much about, and now I'm telling you that this quotient group here is important because somehow its group of connected components is isomorphic to that global Galois group that we're probably going to be very interested in. So let me try and analyze this to give you some kind of feeling for it, right? So here's another lemma of a similar nature to the one we proved before. I claim that AQ star equals Q star dot the product over all P of ZP star across the positive reals. And that dot means I'm claiming that an element in here is the product of an element in there and an element in there. I.e., in other words, if I've got XP, so that's not good notation now, right? Because I've got an infinite prime as well. So we could call it maybe if XV, right? V is running through 2, 3, 5, ... and then there's infinity at the end. Right, the finite places and the infinite places. I.e., if XV is in AQ star, then there is some lambda in Q star embedded diagonally such that XP divided by lambda is going to be in ZP star for all P. And X infinity divided by lambda is positive. So this is of a very similar nature to the thing we did earlier. It's not a coincidence that I did the earlier thing, right? So we've got some random idel about which we know nothing other than the fact that it's an idel. So what do we have here? We've got an XP for each P. We've got a random p-adic number. But the thing we know is that it's never 0, and all but finitely many of them are in ZP star. That's a start, right? All but finally, many of them. This says for all p, but at least we know that for all but finally many of them, we're OK. And then we've got a condition at infinity as well. So how's this proof going to go? So it's going to be induction on the bad set again, right? So I've got this xv in AQ star, some bad set, right? S equals the primes p such that xp is not in zp star. Okay, and we're going to prove it by induction on S, right? Right? And if S is empty, then there's only one thing we need to do. If S is empty, then this is true, and we just have to sort this out. We just have to make sure that we find a lambda in the rational numbers. Remember, all the xp are already in zp star, so we've got to be careful. We can't choose some random lambda. We want to make sure that they stay in zp star. So we need to choose a lambda that doesn't have any prime factors, basically. And we need to make sure that it has the ability to switch positive and negative if necessary. So if S is empty, then lambda is plus or minus 1, right, depending on the sign. Depending on the sign of x infinity. Depending on the sign of x infinity. So that's done, S is empty. And now what about general S? General S non-empty. Well, if S is non-empty, then it contains something. So we choose some prime P in S. And now, what's the problem? Why is P in S? It's because XP is being naughty, right? It's because XP is in QP star, but probably not in ZP star, right? That's why this prime number P is in S, because XP is not being well behaved. So we need to fix this, right? We can write XP is kind of P to the power of n times a unit, right? With a unit in ZP star and n an integer. Okay, and so let's just set lambda as p to the power n, right? So lambda is in z r star for all r not p, right? And lambda's positive, so it's not even going to mess with what's going on at infinity, you see. And now let's just divide by lambda, right? X divided by lambda, so S gets smaller. Right, this is the same kind of argument as I did in the additive case, so I'll just leave it like this. I change x by dividing it by lambda, so all the xv's get divided by lambda, right? All the xr's for finite primes r and x infinity. But the point is, if that used to be positive, then it's still positive, because lambda's positive. And if it used to be in ZR star, you're still in ZR star because lambda's in ZR star. In fact, the only prime really where this messes you around is P, right? This is positive at infinity, and it has R adic valuation 0 for all primes R not P. But at P, it really changes something, and XP divided by lambda is P to the nu divided by P to the n sub u, right? So when you do this, it fixes the problem at P without introducing any new problems elsewhere. Okay, so here's sort of an interesting. So that's the end of the proof. And remark is if K is a number field. Remark 1 is if K is a number field, this is harder to push through. Harder to push through. Okay, because here's the problem. You have kind of X curly P. This is problematic. You have a problematic. You have a problematic curly P, and let's say kind of X. Let's say the p-adic valuation of X curly P is 1, right? So then I want to choose lambda. I want to set lambda in K star, and I want to make sure that kind of lambda, OK lambda is P, right? That's kind of that's the analog, you know. Or if you, well, let's do it perfectly. Like the XP of let's say is n, then I want lambda in K star, and I want this to be P to the n. Right? So this is really what I want, because I want to divide by lambda, and I want to fix the problem at P, and I don't want to introduce any new problems anywhere else, right? If this is P to the n times some other random prime Q, that's all well and good. It will fix the problem at P, but it might cause a problem at Q. Okay? So that's what we need to make this argument work, but hang on a minute. But what if What if p to the n is not principal? Ouch. If p to the n isn't principal, we can't do this. So the lemma's not true, right? So I'll state. I'll just leave that there because this is what I'm leaving the statement of the lemma. So the kind of the fun exercise is that a k star, if I mod out by all this stuff, k star and the product over the finite places p of OK p star, and what am I doing at infinity? Let me just throw everything at infinity, like just all of k infinity star, if you like. That quotient group there, you see, if this lemma says that if k is q, this group is trivial, because I've quotiented out by all the thing on the right-hand side. I've even made it a bit bigger, because I didn't take the connected component, I took everything. So this thing here turns out to be canonically isomorphic to the class group of k. Kind of crazy thing. So the class group of k is somehow embedded in this. That's an interesting exercise. And if you know about narrow class groups, things generated by totally positive units, if you replace k infinity star, if this goes to k infinity star circle, you get the narrow class group. Ideals modulo principal ideals with a totally positive generator. So the narrow class group of the rationals is 1, because every ideal has a totally positive generator, namely the positive integer that generates that ideal. So it's sort of funny that you see these things in there. So you can see that. Oh yeah, the other thing, there's two things I wanted to say about this lemma. That's the reason I didn't raise it. The other reason is, if you think about it, we got away with this by the skin of our teeth. At the end of the day, how did I prove this? I took a random element here, and I'm saying, now let's fudge it by a rational number called lambda, and let's make sure we're in here. When you think about it, what I did with lambda was I looked at what was going on at p, and I saw instantly what I needed to do at p, right? What's going on at p? I need to force lambda to be p to the n times something. And if you look at all primes p, that tells you what lambda has to be at all primes p. So it sort of tells you lambda up to sign. And then if you look at infinity, it tells you the sign as well. So I get away with it by the skin of my teeth. In fact, we showed that AQ star is just isomorphic as a group to the product group, right? When you have a group and two subgroups, and the subgroups commute, and every element of the group can be written as an element of one subgroup times the other one, and if furthermore those two subgroups have trivial intersection, then this big group is kind of abstractly isomorphic to the formal product of the two small groups, right? Canonically isomorphic. Right? This is a product of groups. And the reason it's true is because what stops a random group generated by these two subgroups from being a product, what stops that happening is that we're in the abelian case, right? So there's no issue about groups generated by we're in the abelian case. So I prove that every element here is something here times something in here, and furthermore, I claim that everything in here and here, because Q star intersect the product over P of ZP star across the positive real. So what do I mean by intersect, right? You see, I'm regarding both of these things as living in the adels of Q star. And I'm regarding Q star as being embedded diagonally, and I'm being this stuff here is embedded in the obvious way. So this means what rational numbers are there, which for every prime p, they have p-adic valuation 0, and they happen to be positive when considered as real numbers, right? This thing here is the lambda, such that the p-adic valuation of lambda is 0 for all p, and lambda is positive, right? And p-adic valuation of lambda being 0 for all p means that lambda has no prime factors, right? The ideal generated by lambda is the whole ring. Lambda is a unit, right? And what are the units of z? So this just says lambda is plus or minus 1. And this says lambda is positive, you see. So lambda is plus 1, only solution. That's the identity element in this group. So every element in this group is something in here times something in here, and furthermore, that decomposition is unique. And so do you know what we have here? We've got something for free, right? We've now worked out what the quotient is. So a corollary, something for free, AQ star, modulo Q star, is isomorphic as a topological abelian group to this less scary thing. No random S's, no all but finitely many. It's an infinite product, but there it is, right? So there's AQ star over Q star, and you can really see now, so remember this was something I called C of Q, right? This is this connected component that is stopping. Why can't this group on the right-hand side be a Galois group? It's because it's not totally disconnected. There's this huge connected chunk here, right? So there's CQ, this thing that's stopping it. And this is closed now, right? This is Hausdorff. A point in here is closed. A point cross this random thing. That's a closed thing, right? A point is closed here. This whole set is closed here. So that product is closed in this finite product of this guy and this guy. So CQ is closed. We don't have to take the closure. So corollary, the kernel of RQ is isomorphic to the topological closure of CQ, and it's just, in this case, it's the positive reals, right? The kernel of RQ is this, and so and gal Q bar over Q ab, gal Q bar over Q abelianized is canonically isomorphic to what we have left, product over P of ZP star, right? And some people might want to write that as there's something called Z hat, which is the product over all P of ZP. Z hat star. Right? And another way, I can even write that as a projective limit. So gal Q ab over Q is canonically isomorphic to Z hat star, which is the limit of Z modulo N Z star, right? And the definition of an infinite Galois group is the limit of finite Galois groups, right? So this Galois group here is supposed to be the limit there for L over Q, Galois and abelian of L, gal L over Q. By abelian, I mean that it's Galois and the Galois group's abelian. So these limits are supposed to be the same. And why is that happening? That's because for every n, this is a limit over n positive integers, right? For every n, there should be some Galois group here whose Galois group is canonically Z mod n Z star. And guess what it is? It's Q zeta n, right? Gal Q zeta n over Q is canonically Z modulo n Z star. And although this isn't a proof, this is huge, you see. So these must be the L's, and this Q ab is a union of the L's. So this is evidence to suggest, although it's not really a proof, this is evidence to suggest, looks like Q ab is the union of Q zeta n's. But you see, I keep saying, oh, this is canonical and that's canonical, so all these diagrams must obviously commute. But of course, at the end of the day, one has to check something, right? But this is true, right? I don't really have a good feeling as to... my guess is that even if you assume the statement of global class field theory as I've told it you, my guess is that you can't really formally deduce this. I might be wrong. But how do I know that all these canonical isomorphisms are all the right?
I'm saying that first project gal.
Yeah, gal Q ab. We can define this field to be Q sick.
Yes.
So, and certainly Q sick lives in Q ab.
So this is
So there's a surjection from gal QAV over Q to Q sig over Q. And Q sig over Q, the Galois group is canonically Z hat star. So now we have a canonical map from Z hat star to Z hat star.
So if you knew it was that diagram computed.
I can kind of believe that this might work. And that there might only be the only map from Z hat star to Z hat star. Maybe all maps from Z hat star to Z hat star are isomorphisms. That might be true. And then that would in fact do it, right? Just that might be an algebraic fact. Any surjection from Z hat star to Z hat star might be an isomorphism. I'm going to use Pontryagin duality to prove that. Is that crazy? Anyway, something to think about. I think it's time to tell you what a Grierson character is. Definition. So K a number field. Well, it's called lots of things. I think people used to call it Grierson Charakter. People used to write the whole thing in German. Grierson Charaktere. This is a phrase introduced by Hecker, I guess. But then it somehow became half German and half English. And then, of course, because things with umlauts on are a pain. This isn't one of these. This is two dots, actually. So maybe people started writing, and this funny thing that looks like a beta is an SZ. So people then started writing this. And then sometimes people write Hecker character. But sometimes people use Hecker character to mean something else. But sometimes people use Hecker character to mean another thing that turns out to be canonically identifiable with what I'm about to write. I think I'm going to stick with this one. Do you know what? I'm going to stick with GC. I'm going to call it Grierson character. I'm going to call that Grierson character, but I'm going to write GC because it's going to save chalk. A Grierson character is a continuous group homomorphism. Oops. A continuous group homomorphism from K star over AK star to C star. That's what it is. Okay? And we can write down examples, right? Because look, just right here, I've figured out when K was Q, I've figured out what that quotient group was. Okay? So I've got to write down a continuous group homomorphism from this thing here to C star. And maybe you're a little bit terrified by that thing there, but that's fine. You can just kill it. We set everything to 1. And we just have to now write down a map from the positive reals to C star. That sounds plausible, like the inclusion, that would work, or like squaring. Take the square root, that would work. We're going to be able to write these things down. This is a useful thing to have around because we want to become friends with these guys. Why do I care about Grierson characters? There's a secret about Grierson characters which you're not allowed to know until a couple of days' time. So let me leak the secret. So here's a leak. Grierson characters are automorphic representations for GL1 over K. And there's a global Langlands correspondence which says things about automorphic representations relating to Galois representations. And I did all the Galois representation stuff yesterday. So that's what's happening. And we have to figure out, this is Langlands insight, right? And now we have to figure out how to change the 1 to a 2. And so we change the 1 to a 2. When we get GLN over K, we're going to end up with maps from GLN of K over GLN of the AK, right? To C. So blah, 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 right? That's where we're going. So that's right, you can forget I said that. But by the end of this 2-week thing, we'll have seen a whole bunch of, everything will join together, right? That's the plan, is that at the end of it, there should be some coherent story that I'm telling. And I've told you the local Langlands conjectures, and we're going for the global Langlands conjectures. And the local Langlands conjectures for GL1 were just something about characters of groups that were showing up, and it was just a triviality from class fill theory. So now we have to figure out what the global Langlands conjectures are going to say for GL1, because I've just given you a little hint as to what the object. We've seen the objects on both sides. Right? The object on one side is these continuous group homomorphisms, and the other side is going to be representations of Galois groups. And we've seen, I did all that stuff yesterday about families of L-adic representations. So there you go. So there's a hint of what's to come, right? So there's global Langlands for GL1, there's global Langlands for GLN, and that's the end. So we can see the light at the end of the tunnel now. Let's do examples. Right? Because this is a really scary definition. This is a scary object, so this is a scary definition. Right? Let's just do K equals Q, because K equals Q is nice and easy. Okay, Q star modulo AQ star. We know that this is Z hat star cross the positive reals. So there's two parts to this. If I want to give a group homomorphism from A cross B to C, think about it, right? This is a group, continuity, whatever. This is a group homomorphism from a product of two groups. I've got to give a group homomorphism from A cross B to C star, okay? And to do that, all I've got to do is give a group homomorphism on A and a group homomorphism on B, and then multiply them together, right? So if I want to tell you all the Grierson characters for Q, then all I've got to do is I've got to figure out what all the continuous group homomorphisms from this guy to C star are, and all the continuous homomorphisms from this guy to C star. And then we'll actually know all the Grierson characters. I'll rub this. This is confidential information, so I think I better remove it. There. Leaks are a thing now, aren't they? It never really occurred to me how they happen, but I'm beginning to learn. Right, so Z hat star, you have to find the leaker. Right, so as I just said, we need to figure out there. So here's some kind of nice, pleasant lemma. It's an tedious exercise. The continuous group homomorphisms from the positive reals to C star. I'm not going to prove this. Are all of the form x maps to x to the s for s a complex number, and the definition of x to the s is exp of s log x. In fact, the fact that I'm using exp and log is a clue as to how to do the exercise. Right? You use exp and log to reduce the question to figure out what the continuous maps are from R to C, basically. And every continuous group homomorphism from R to C turns out to be linear. That's the point. Multiplication by S. That shouldn't go. Sorry. Let's go over here. So that's what the continuous group homomorphisms are on the positive reals. So basically, they're controlled by one complex number. So as the data for a Grierson character, I need to give you a continuous map from this to C star and a continuous map from this to C star. Okay. Now, what the heck is this Z hat star? Is the scary part. So Z hat star, but this is remember, I've got a continuous map from this to this. C star contains no small subgroups. Right? If I've got a tiny little open neighborhood, there exists a tiny little. Here's a picture of C. Here's a picture of C star. There's the number 1. Here's a tiny little area here. That tiny little area there is an open set, and that open set, when you think about it, contains no subgroups, right? That little disk is the open disk, center 1, radius 0.1. Okay? That little open disk there, the only subgroup the only subgroup of C star living in there is the identity. C star has the no small subgroups property, right? The moment you take some random thing that isn't 1, it's 1 plus epsilon, you raise that to the power 1,000,000, it's going to fall out of that little circle. So C has no small subgroups. So I can take this open set, and I can look at the preimage of this. So I'm now trying to work out maps from Z hat star to C, right? If I've got Z hat star to C star, let's say whatever. They've got some alpha. Alpha, a continuous group homomorphism. Okay? So take U living in C star, the open disk, right? Center 1, radius 0.1. Or some sufficiently small number. So U is an open set, right? Alpha inverse of U is going to be open. Okay? And it turns out, what's a basis of open neighborhoods? Because you see, Z hat star is the limit of Z mod NZ star. Okay? And this defines the topology, right? So alpha inverse U open, that implies, if you don't really understand limits or these infinite products, this is what you need to know. Alpha inverse of U is open implies alpha inverse of U contains the kernel of this map, right? Contains the kernel of this map here, of Z hat star to Z mod NZ star. Z mod NZ star is a finite group that we all understand, right? This is open, so it contains the kernel of this map for some n. Okay, and that kernel is a group, right? So the image of this group, okay. So let me call this Kn, right? So Kn is this kernel. I'm trying to figure out, what am I doing here? I'm trying to figure out the continuous group homomorphisms from Z hat star to C star. Okay, and that's really important because there's this leak that this thing here, there's supposed to be automorphic representations for GL1, but we're currently working with continuous group homomorphisms. I'm trying to understand them all. I want to understand every automorphic representation for GL1 of OK. So I need to understand all the continuous group homomorphisms from Z hat star to C star, and I'm just saying that by general unraveling definitions, one sees that the continuous alpha from Z hat star to C star, the image, there must exist an n such that so there's this kernel of this map here, right? Such that Kn, alpha of Kn, must land in this tiny open subset. So it doesn't really matter if you don't follow this, because what you need to understand is the conclusion. So if you don't know this, if you're not too happy with this machinery of infinite limits and blah, 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 but the point is, so we have Kn, alpha of Kn is now living in U, right, and is a group, right? So therefore, alpha of Kn is a subgroup of a thing that doesn't have any subgroups. So it's this, right? And therefore, alpha factors as Z hat star, the terrifying profinite thing, surjects on to Z mod NZ star, and now we must have a continuous group homomorphism from this topological group with the discrete topology to C star. And such a map here, that's called a Dirichlet character, okay? And we understand it. So that's great. So what we've done, what's the upshot? We've really proved something. A Grierson character for Q is a map AQ star over Q star to C star there. And it must be of the form. And on the subgroup Z hat star cross the positive reals, it sends, well, I've got my quantifiers in the wrong order. So I've got a Grierson character, I'm going to write that again in a minute, is this. And for each such Grierson character, And for each Grierson character, there exists a pair, chi, comma, s, where chi is a Dirichlet character, and s is a complex number, and this Grierson character is just made from chi and s, right? Such that, and the Grierson character on the subgroup z hat star cross the positive reals. I'm only telling you what it is on a subgroup, but that's okay because it turns out that that subgroup, the natural map from the subgroup into this thing here is a bijection. So all I have to do is tell you what the Grierson character is on the subgroup. And the Grierson character on the subgroup sends whatever, factors through as it's z hat star cross the positive reals. That maps down onto z mod nz star cross the positive reals. And then finally, we send n, comma, x. That ends up mapping to the complex numbers via chi of n multiplied by x to the power s. That's what they all are. So there's all the Grierson characters. To give a Grierson character is to give a Dirichlet character and a complex number. So here's a crazy observation due to Tate. Not really ever explicitly made. No, it is explicitly made, but not really flagged in his thesis. Right? So here's a corollary. The set of Grierson characters for Q, that's a set, right? It's just the set of group homomorphisms from X to Y. This set of Grierson characters for Q has the structure of a Riemann surface. Of a really topologically dull Riemann surface. Okay? Because you have a pair, chi and s is in the complexes, so S has a Riemann surface structure, and chi is a discrete object, so it's not going to move, right? So you fix a chi, fix a Dirichlet character chi, right? And then I've got a map. C injects into the set of Grierson characters, right? I'm just going to send S to the pair chi, comma, S. And these maps are injections from C in, and if I take the union over all chi, then it covers, right? So every single point, I've given a little neighborhood of that point, I've given it a complex structure. A point in here is a pair chi, comma, S, and I'm going to say a little neighborhood of that is chi, comma, S plus epsilon, where epsilon is a small complex number. That's how you get your, Riemann surface. So this is an eigencurve, right? This is an eigenvariety. This is a complex analytic eigenvariety. It's the first one in the literature, and it's due to Tate, right? So I'll tell you in Tate's thesis. He takes a Grierson character. Let's call it, I don't know. Let's call it psi. And he defines L of psi. I thought he was going to define L of psi, comma, S when I was reading Tate's thesis. Given a Grierson character, because a Grierson character is kind of a generalization of a Dirichlet character. And Dirichlet characters have L functions, right? And a Grierson character is, in fact, an automorphic representation for GL1 over the Adels, right? And automorphic representations have got L functions. So Tate takes a Grierson character, and I expected him to attach to this Grierson character a complex number, and he defined a number by an integral. And the integral didn't even always converge, but for certain Grierson characters it converged, right? So a number, not a function, okay? And that gives you a function from this Riemann surface. So L is now a function on the Riemann surface of all Grierson characters, right? and it's only defined on a subset, but Tate proves that this function is holomorphic and has a meromorphic continuation to the whole thing, right? So why don't I call this the complex analytic eigencurve? I'll just call it I'll do it, right? The complex analytic eigencurve for GL1 over Q. So Tate defines a number, and that number, so it turns out that L is meromorphic, right? Has a meromorphic extension to all of the C eigencurve. To all of the C eigencurve. Right? And that meromorphic extension, remember, how did I define that Riemann surface structure? When I fixed a Dirichlet character chi, I ended up with a copy of the complex numbers in this C eigencurve. And that copy of the complex numbers has now got a function on it. And that's the L function of chi. Right? That's the classical L function of chi. You see? L, one can check. So Tate checks the L of this function here, right? That if the restriction of L to this kind of to the copy of the complexes attached to chi is L chi comma S. Right? So if you like, explicitly, L of chi comma S is L of psi, where psi is the Grierson character attached to the pair chi comma S. This is not a part of Tate's thesis that is ever solved particularly well, in my opinion. The reference for that observation is Tate's thesis. This has been a hugely inspiring thing for me. This has somehow shaped how I understand the conjectural theory of p-adic automorphic representations and what that theory should do and where it should live, and it just helps me understand L functions in general. And it's embedded in a remark in a 1950s thesis that was never published for 20 years or something. And I just think I don't know. For me, this is an important thing. Generalizes to, let me just generalize it to, one of the great things about Tate's thesis was he generalized all of Hecker's work about attaching L functions to a large class of Hecker characters, basically. So I've just done all this for Q because I think it's the easiest to understand. Generalization to K, right? Do you remember at some point I made a huge amount of fuss about something else that sounded completely silly, right? Recall for K over, so now I've got some local, I don't really want to call it K now. Shall I call it K curly P over QP finite? So this K curly P is the K from last week. There's a canonical norm, right? There's a canonical norm, right? And the norm of the uniformizer at P is 1 over Q. The norm of a uniformizer should be small, and it's 1 over Q, where Q is the size of the residue field. Okay? And that has been normalized in the right way. When I was talking locally, I just said there's a clever way of thinking about it in terms of additive Haar measure. Right? Multiplication scales the additive Haar measure by some value, and there's my norm. Okay, but the Adels are locally compact, and you could do some global calculation. I've just told you something that generalizes, and this trick, this canonical norm trick, extends to the Adels of K, right? Take some Haar measure, right? So Haar measure, there exists, it doesn't matter if you don't understand this, there exists a Haar measure on the Adels of K, and multiplication by some random element, x in the Adels right? Multiplication by x in this gives me a map from AK to AK, and it scales the Haar measure. This is an additive Haar measure. A multiplication by this thing scales the additive Haar measure by a canonical norm, right? Right, and that's a positive real number. Okay? So what I just did there was I said you can use black magic to define a norm on AK star. Okay? So black magic gives us a norm from AK star to the positive reals. Okay? And that black magic, this contains K star, right? So black magic gives us a canonical map from the units in any number field to the positive reals. And there is no such canonical map, right? How can I possibly take some, like Q of I, where's the canonical? It just seems extremely unlikely that such a canonical map should exist. Q root 2, how am I going to attach a positive real number? I don't know. So this is a subset sign. AK star contains K star. And so the only possibility for this black magic map on K star is it must be the trivial. I just wrote that. It must be the trivial homomorphism, right? That's not a proof, but somehow this thing here from K star to the positive reals turns out to be trivial. So, yeah, always diagonal. Always diagonal. There. So let me just show you explicitly, if K is Q, let me show you why that's true, right? Let's work out this global norm of 3/4. Okay? So the idea is this global norm is the product of all the local norms, right? Okay. Because the global and local norm, that's really worth saying, right? This comes from the black magic, or this is either a fact if you believe in black magic, or it's a definition if you don't, right? If you don't believe in black magic, then I'm going to define the norm. So X is an idel, and I'm going to define its norm to be simply the product over all V of the canonical local norm at V, right? Because there's canonical norms on the real and complex numbers and canonical norms on these p-adic numbers. And all I'm doing is I'm doing this. And that looks like a scary infinite product, right? But it's a finite product. It's a finite product. It's a trick. Because the definition of the adels, the definition of the idels is that these xp's have to be in OP star for all but finally any p, and so they've got norm 1, right? This is a finite product. And let's work it out here then. This thing here is going to be the product over all primes p of the norm of 3/4 of p times the infinite norm, right? 3/4, the usual infinite norm. So what's this norm? So this is the p-adic norm. You see what I'm doing? I'm taking a random rational number, and I'm taking its p-adic norm for all primes p, and I'm taking its usual norm, and I'm going to multiply them together. So lo and behold, what's the 3? Well, this is like 3 times a unit, right? So the 3-adic norm of this is small, right? This is 3 times a unit. So the 3-adic norm of this is a third, right? That's what's going on at 3. And the 2-adic norm, this isn't even an integer at 2. We have 4. This is huge at 2, right? We have 4 in the denominator, and the norm of 2 is a half, yeah? This careful normalization, has it gone? There, the norm of pi is 1 over q. So when you translate that down to the p-adic numbers, I get the norm of 2 is a half. So the norm of a quarter, the norm of 3 is 1, of course, because 3 is odd. And the norm of a quarter is 4. So this is 3 times 4. That's what's going on at 2, times loads of 1s, p bigger than root of 5, times what's going on at infinity, which is 3/4. And it all cancels. Isn't that great? Here's 1. Right? So that's why the norm of p, the periodic norm of p is 1 over p. And then the infinite norm of p is p, and then everything cancels, you see. So that's the proof that works for Q, and now you can have a proof over K by doing some cheating with norms. So there's my global norm. And even if you don't understand it for a general K, you understand it for Q, because that's a proof, right? 3 and 4 are random variables there, and the prime's dividing 3 and 4. Right? When I say 3, I don't mean the thing that you think of as 3. I'm using 3 as a variable for an arbitrary positive integer, you see. So there you go. Right, so there we go. So the upshot here is that there's a norm. This canonical black magic norm is actually a function here, right? Well, positive reals, right? So this is a kind of a global. This is a weird thing. This is non-trivial on every periodic field, right? This restricts to the periodic norm on all KPs, right? There, and it's the usual norm on the reals. At infinity, there's some R stars in here, but the usual norm of the reals, right? The norm of a negative thing is positive, right? And it's the square of a usual norm. The norm of x plus iy is x squared plus y squared on C. That's what you get for the complex numbers. Because when you think about it, the multiplication by 2 on the complex numbers, multiplication by 2 is scaling by a factor of 2 in 2 dimensions. So it sends something that has area x to something that has area 4 times x, right? So the canonical norm of, if you think about it with this black magic method, the canonical norm of 2 is 4. So that's what happens. So we now have an analog of what we had for the rational numbers now, you see. We've got this random thing, and so now you can do the same story, right? So hence the set of all Grierson characters for K, for GL1 over K, if you like, also gets the structure of a very, very uninteresting topologically Riemann surface, right? Also becomes a hugely disconnected Riemann surface, okay? It's just an infinite disjoint union. Still looks the same. Infinite disjoint union of copies of C, right? And so how do you know when two things are in the same? If I've got psi 1 and psi 2, these are maps from K star modulo AK star to C star, okay? These are two random Grierson characters. When are they even in the same connected component? Are in the same connected component if and only if their ratio, psi 1 over psi 2, turns out to be the norm character to the power s for some s, right? And that s is the parameter on the complex plane that they're in, right? And so you could write, so psi 2, whatever, you could write psi 1 goes to some number z in the complexes, and then psi 2 goes to, I guess it would be z minus s, unfortunately. That's the idea. There's my Riemann surface structure, right? Neighborhood of, a holomorphic neighborhood. A holomorphic neighborhood of psi 1 is psi 1 times norm to the s, there, for s in some closed disk, radius epsilon, right? That's my complex structure near L1. My complex structure near L1, I'm saying that it looks like the open unit disk, and here are all the points that correspond to nearby nearby elements of the open unit disk. So there you go. So there's Tate's thing, right? And then Tate's thesis, the main point of Tate's thesis, he defines one meromorphic function on this Riemann surface. That's all he does. Oh, and he improves functional equation, I guess. Functional equation relating this L of psi to L of 1 minus psi, which I guess means the norm character to the power 1 divided by, for a general Dirichlet character, you've got to be careful, haven't you? For a general Dirichlet, it's somehow L of something else. I'm not going to do it. It's a functional equation. There you go. Because it involves the dual, doesn't it? I think it involves, psi. Somehow it involves psi1 complex conjugate. I didn't prepare this, so I don't want to write down the wrong thing. It's going to relate L of it's going to end up relating L of psi is going to be related to L of psi bar, but possibly times some norm or something. I'm a bit unclear. I'll need to sort that out. It doesn't really. You see, I don't really care about L functions. That's the problem. What I care about is the spaces. And Tate invented eigencurves. That's what I'm suggesting in the complex analytic world. You see, because I'm telling you that these Grierson characters are automorphic representations for GL1 over Q, GL1 over K. And now I'm seeing, actually, they have a geometric structure. So what's supposed to happen is there's supposed to be p-adic automorphic representations, e.g. p-adic modular forms or whatever, and those are supposed to maybe come in some p-adic parameter space, and that would be your eigenvariety. And that's exactly what's happening for GL2 over Q anyway. So there we go. That's sort of an interesting thing, I guess. Oh yeah, go on.
Riemann surface uncountably infinite?
I think it's countably infinitely many copies of, because you end up with what I proved to you that, fair enough, I'll tell you epsilon more. So Q star over Q hat star was the product of, this is a pro-finite thing across the positive reals. Okay, so it turns out that K star over AK star looks like is very closely related to this product P of OP star. So this is very vague, but it will give you some kind of way of thinking about the question. So you get some analogous pro-finite thing. So that, as a set, is uncountably infinite, but it has countably infinitely many characters. Because like the characters of this were Dirichlet characters, so there's only countably many of those. And then what's going on at infinity? You have this kind of R. Remember we had R stars and C stars, right? And C star is topologically S1 cross the positive reals by polar coordinates, re to the I theta. The theta is a circle, and the r is a positive real. So we get some S1s, and we also get some positive reals to some power, right? R1 plus R2, because for each real number we get 1, and for each complex number we get 1, yeah? But now this isn't quite true because there's global units that are in K star and in this stuff here. So this is modulo some lattice, z to the R1 plus R2 minus 1, because that's the rank of the global units if you know these things. So lo and behold, we get some product of P of OP star, so some compact pro-finite thing, times kind of S1 to some power, and we get one copy of the reals, because you see the R mod Z is another S1, right? And then we get one more positive real. And that's the S parameter that you get from the global norm. And so your question is, how many characters are there of this gadget here? And the characters of a pro-finite thing, there's countably infinitely many. In characters of S1, they're all Z goes to Z to the N. So again, there's countably many. So it's countably infinitely many compact Riemann surfaces. And now I've pretty much told you everything I know about Tate's eigencurve, actually. This is a heuristic. It's much more subtle than that because the embedding of the global units is kind of diagonal in some slightly scary way. So one has to be a little bit careful. But this is heuristically, that's what's going on. So, I need to kind of tell you about the global Langlands philosophy. We haven't really, let's try and, so as I say, there's been this leak that says these are supposed to be automorphic representations, which means we should be able to associate Galois representations, right? So let's say I've got some random automorphic representation for GL1 over Q, right, is a Grierson character. So it's really nothing more than a pair of Dirichlet character and a complex number. So let's say chi is trivial, and let's say S is, I don't know, the square root of minus pi. The pi is not a very good, the E, that's a random, there we go. So there's my number. Okay, so that's a random complex number. So attached to that data, by the global Langlands philosophy, there's supposed to be a Galois representation. And this Galois representation has to be arithmetically completely trivial, and it has to somehow take into account the fact that part of this Grierson character contains an arbitrary complex number. So is there a Galois representation? Is there a Galois representation attached to chi? Attached to psi, right? Of course there cannot be, right? There cannot possibly be any kind of sane Galois representation attached to a random complex number, right? Forget about the Dirichlet characters. Given a random complex number, how am I going to get a Galois? So what are the global Langlands conjectures? So this is when we see the lie, right? So here's the idea. There exists a global Langlands group, right, that nobody has a definition of. Okay, LQ, right, or LK, right, LK for general K. And the idea is that my automorphic representation for GL1 over K should correspond to a representation of the global Langlands group. Okay, so a one-dimensional representation of the global Langlands group. Okay, and so LK abelianized. Oh, look, that's going to be K star over AK star. Let's just say that the global Langlands group has that property, because the global Langlands group is supposed to have that property, right? The global Langlands group will have this property. Okay? Because the global Langlands group is a group that we have no definition of. I've stressed this before. There is no definition of that global Langlands group, right? You can read a paper of Jim Arthur where he claims to give a definition of the global Langlands group. But all he does is he assumes the global Langlands conjectures for GLN. And then he builds a very abstract group about which you can prove essentially nothing. Okay? So the global Langlands group is currently a lie. And, but it's when we discover it, when we write down its definition, it will have this property, right? And so now we're going to get this amazing theorem, a profound mathematical theorem, that there exists a canonical bijection between automorphic representations of GL1 over K. There, these are going to match up with semi-simple one-dimensional representations of the global Langlands group of K, right? That's a theorem, and the reason it's a theorem is because by definition, what is this? That is just, I've told you, it's a Grierson character, right? Psi from K star over AK star to C star. And how am I possibly going to get a representation of this global Langlands group? It's going to go LK to LK ab, right? And that equals K star over AK star, and there's psi to C. So there's the proof of the global Langlands conjectures for GL1. right? It's content-free. In contrast to the local Langlands conjectures for GL1, the local Langlands conjectures for GL1 actually contain class fill theory, right? Local class fill theory says these things match up. I want to use global class fill theory to prove that this global Langlands group abelianized is this. And I can't do that because this global Langlands group doesn't exist. You know, I want to kind of use global class fill theory, but global class fill theory says, oh, this has something to do with the Galois group. So I need to write some clever, you see, I need some, remember the Weil group, I guess that's the point. Remember that local Weil group? I just wrote it down. I said, look, it's a subgroup of the Galois group. So I need to kind of do the same thing here. I need to write down a global Weil group and then a global Langlands group, which is like a global Wedelin group somehow. So anyway, the whole thing is a lie. Sorry, by a lie, I mean a really important motivating picture. That's what it is. It's a really important motivating picture. Because it means the Langlands group, if I have L over K as a finite extension, then the Langlands group of L should live in the Langlands group of K, which means that given a one-dimensional representation of the Langlands group of K, I can restrict it to the Langlands group of L. Okay? And a restriction on that side should correspond to some kind of construction where given an automorphic representation for GL1 over K, I should be able to make an automorphic representation for GL1 over L. Right? If L over K is a finite extension, then by this philosophy, given an automorphic representation of GL1 over K, I should be able to get an automorphic representation of GL1 over L. And lo and behold, there's a norm map here. Right? And there it is. If I've got one of these, I do the norm map and I get one of these. So there is my base change of chi from K to L, right? That's all it is. It's the norm map for GL1. No, that's not base change. That's the other thing, right? That's what is it? No, it is base change. Is it base change? What? Yeah, this is base change. Why did I call that other thing base change? That was automorphic induction. Ooh. Base. I suddenly don't know what base change is. Let me call it base change. I think I've given you, although I haven't said anything false, I think I've given you kind of incompatible words. Anyway, I've got 2 minutes to go. Is there anything worth saying? Oh, yeah. So there's something wrong, right? How can we? The problem is we're going to generalize all this to GL2. And we want to prove something, right? Or at least we want to say Deligne proved some stuff which can be interpreted. We're in real trouble here because we can't interpret this, right? Let's change all the 1s to 2s. We have all more representation of GL2 over K. That has a definition. I'll give you that definition tomorrow. And that's supposed to then correspond to two-dimensional representations of a group we don't know and a group whose abelianization. If we change the 1s to 2s, we're in trouble. We can't define this side at all. So this theorem here isn't going to generalize, right? It generalizes to a statement that we can make no sense of at all. So we need another idea, because, I mean, otherwise I could just spend the last 3 days waffling on and saying this is what the global Langlands conjectures say. By the way, we can't even define the right-hand side. It's kind of difficult to, makes these things unprovable. So there's a trick, right? And I chose this random complex number here. So here's something to think about over the next 24 hours. If S was actually an integer, somehow, life would be a bit better, right? And I'll tell you why life would be better, because then, let's have K as Q, and then psi, this random Grierson character, this Grierson character for GL1 over Q, is a pair chi, S. Okay? And now chi is a Dirichlet character, right? Chi goes from Z mod NZ star to C star, but when you think about it, that its image is really E, right? E0, right? E0 is Q whatever, some zeta, some appropriate zeta, right? Living in the complex number. The image of that Dirichlet character is in a number field, right? And this, of course, is gal Q zeta n over Q, right? So given a Dirichlet character, I get a one-dimensional representation to GL1 of a number field, and I can complete that number field, right? So chi gives chi lambda from gal q bar over q to GL1 of E0 completed at lambda, right? If E0 is just the rationals, then this is just the p-adic numbers, right? And that's a compatible family, a compatible system of lambda-adic Galois representations. So if S is 0, then given a Grierson character psi with S is 0, I can actually get something that has some meaning, right? It's a compatible system of lambda-adic Galois representations. And now what about if S isn't 0, but if S is, let's say, what about if S is an integer? What about if S equals 1 and chi is trivial? Then S equals 1, then this Grierson character is just the norm to the power 1, right? And so the norm of some uniformizer at P is somehow 1 over QP. And this kind of looks a bit like, the cyclotomic character. I guess up to twist. Yeah, there's a switch. I like the idea. You see, I know other systems of compatible lambda-adic Galois, so I am going to stop. But I just want to write down this one example, right? Another example of compatible system of L-adic Galois representations. I've got gal q bar over q. I've got this omega L, right? This L-adic cyclotomic character to GL1 of QL. These are also a compatible system. And that kind of looks like the norm, right? Maybe that thing there, S equals 1, should maybe correspond to the cyclotomic characters, right? And maybe S equals n for a general integer n should correspond to the cyclotomic characters to the power n. So you see, I'm trying to save us, right? We can't generalize this, but for certain Grierson characters, the algebraic ones, we do get compatible sequences of Galois representations. Will that work for general Grierson characters? Is there a notion of algebraicity, which just gives us a family of L-adic Galois representations? That's the next thing I'll prove. And then we'll define automorphic forms, automorphic representations, and then we'll state the global Langlands conjectures for GLN. And then we're finished. Is it still Tuesday? Great. We're going to make it. We're going to do all the things I want to do. Did that go all right? That's loads of stuff, right? Tate invented the eigencurve. Who knew?